All right, now, after our last discussion, we were just discussing the basics of heat, giving you some basic introductory information into thermochemistry and giving you a little bit of a peek at the fact that we're going to be looking at changes in heat throughout different reactions, in some cases, sets of reactions. So this is going to be still a little bit more of some theory type stuff. We're not going to be doing a lot of crazy calculations today, but we need to understand that there are two different ways of measuring heat, and they are, as it says here in the yellow, Q, and then also something called enthalpy, which is probably one of my favorite chemistry words because it kind of makes you sound goofy when you say it. Enthalpy. It's kind of a fun one. Say it with me just once. Ready? 1, 2, 3. Enthalpy. See, feels awesome, doesn't it? Okay, moving on. Okay, so this is something that I will ask you to make a note card of, as you can see there in the red. A couple things that we've talked about already. So type of reaction. Remember, we have two types of reactions in terms of thermodynamically speaking, that is, endothermic and exothermic. I have here experimental effect noted. So we talked about this with the last section. Endothermic reactions, you will feel the vessel cool. So if you were holding a beaker in your hand and you did an endothermic reaction, you would actually feel the beaker cool down in your hand. Whereas the exothermic reaction, you would feel that beaker heat up. Now the result of the system, remember the system is something we defined with our last section. The system is actually what's in the beaker, the actual chemicals that you care about. So when you're talking about an endothermic reaction, the result of the system is that you're putting energy into the system, adding energy, and hence the sign of Q. And actually you will also find that the sign of H, which is going to be the enthalpy number that we'll talk about later, is positive. It will be a positive value. Whereas with exothermic reactions, you're actually giving heat away from those chemicals, letting it go into the surroundings. You're removing energy from the system, and so your sign of Q will be negative. So at this point, like I said, we aren't going to be doing a lot of calculations just yet, but I want you to start getting these positives and negatives in your head as quickly as possible, because throughout this chapter, especially as we get towards the end, we're not going to be just dealing with enthalpy, but we're going to be dealing with actually two other things, and the positives and the negatives, they're going to be really important. So first off, get this one in your head, that when we're talking about heat, positive is endothermic, negative is exothermic. And if you would like to, right now, go ahead and pause the video, make a note card of this, and then do me a favor. When you make the note card right here, would you write and H? In fact, let me just go and do that really quick right now. And H. No, that just kind of messed it all up, didn't it? That's all right. I can fix it anyway. Okay, so add that in when you do your note card. I'll tell you what H is in just a second, okay? So pause the video if you need to. Okay, so a couple of examples. When we're talking about using Q or what Q is, we're going to just take a look at this reaction here. So we have CH4. Anybody know what that's called? Hopefully somebody out there said methane. O2. Oxygen gas, and then H2O is obviously water, and then CO2, carbon dioxide. So when you think about this, this would be a combustion reaction in which we are combusting methane gas. If we were able to, at this point know how to do the calculation, we would actually find that 890 kilojoules of heat is evolved when this reaction occurs. The reaction vessel, if we were touching it, would get hot to the touch, and that means exothermic. Again, the word evolved and exothermic, those go together. And that should also be clear too, just by the word combustion, like kaboom, combustion. It gives off heat. It's like a big explosion. It's fire. It's a Bunsen burner flame. It's hot. So it all kind of goes together. Q then is negative. And remember, Q stands for heat. Heat is negative, exothermic, negative, evolved. Okay, got to get all these word associations taken care of. If I take a look at this this equation, here's something fancy. Can you name this part? Hopefully you said barium hydroxide. Now, the next thing I have to ask you is there is this little weird dot thing and H2O. Do you remember what the heck that thing is? Hopefully, you remember a little bit. That's called a hydrate. What it means is that you have one water molecule that is loosely connected to the barium hydroxide part. Basically, it's a hydrated formula, and it's called a hydrate. So this little dot that's right here, it's not a plus sign, but what it is it's showing like a loose attachment. So it's called a hydrate. So the way to actually name this would be barium hydroxide hydrate. If there would happen to be, say, 2 water molecules, you add prefixes. So that would be barium hydroxide dihydrate. Okay, so in this case, it's just barium hydroxide hydrate. And then the next chemical here, what's it? Ammonium nitrate. What is this? Ammonium, water. And then what's this? Barium nitrate. Okay, so if we were able to do this reaction, we would actually see that 170.4 kilojoules of heat is absorbed. So absorbed is your key word that helps you to understand that that reaction vessel would actually be feeling cool to the touch. It's an endothermic reaction, and that means that Q is positive. So these are just 2 examples to kind of show you how these words go together. Also to talk about the numeric value, whether it be negative or positive, of Q. So get all this taken care of, get all this down, because it's going to be really important as we go forth. Okay, so enthalpy now. Okay, we've been talking about heat and Q. Heat is Q. Makes no sense, right? I have no idea why. Maybe something Greek or Latin, I don't know. But heat is Q. Enthalpy is related to Q. In fact, it's related so closely it practically is the same number. But it's denoted, or its abbreviation is capital H. Again, hence the capital H that we started this note card section with here. So enthalpy is H. Why? I don't know. I mean, there's an H in the word. Maybe that's why, but I don't know. Capital H, it's enthalpy. The definition of enthalpy is, if you'd read it with me, it's an extensive property. What that means is that it depends on the amount of the sample. In other words, if you would try to boil a teeny little bit of water versus a whole bathtub full of water, you're going to have to put more heat into the bathtub full of water because you have more substance, more of the sample. So enthalpy works that way. If you have more of something, then you can get more heat from it. But if you have less of something, you get less heat from it. Kind of makes sense, I think. So again, extensive property. It can be used to obtain the amount of heat evolved or absorbed in a chemical reaction. So it's, again, basically Q. If I want to put this definition in English, however, just to make it a little bit easier, enthalpy is the measure of the amount of heat exchanged in a chemical reaction. So a heat exchange occurs within chemicals, sometimes within the surroundings and the system. So it's just a measure of heat exchange. That's all it is. It is called a state function. And this is something that you'll want to kind of keep in mind too, a state function. It depends on the initial state and the final state of the reaction. A good way to explain this would be, and it's going to be sort of a weird correlation, but just kind of go with it. You may want to go to Defiance. So we're going to drive from Napoleon to Defiance. Obviously, there's like the fastest route, right? Probably hop on 24 and you'll be there in a few minutes, no big deal. However, maybe today I don't feel like going the fastest way and I decide I want to go kind of roundabout and take some country roads, and eventually I get myself to Defiance. Well, if you think about that in terms of energy and enthalpy, it doesn't matter whether I go the shortest distance or whether I go kind of roundabouts, I will still require the same amount of energy to do either one. And I know that sounds a little strange, especially when you think of like being in a car and, you know, you use more gas and stuff. But it depends on the initial state, in other words, the initial reactants, and then the final products that you actually make. So whatever you start with and whatever you make, that's really all that matters. And all the in-between steps, it doesn't really matter how many steps you take to get there, because you're always going to bring it back to the same amount of energy, even if you did it in a faster way. This will, and I guess this is pretty much what I just said, depends only on the initial reactants and final products. How you get there makes no difference. It's just that you get there. So it's the whole driving example is maybe a little bit dicey just because of the idea of gasoline and such. But when you talk about chemicals, it really just matters what you start with and what you're trying to make at the end. How you get there makes no difference. So you will start to see that actually as we go forward with some of the mathematics stuff later. So when we talk about relating Q and H, Q again, remember, is heat. H is enthalpy. And these two things are very closely related. In fact, they're not just very closely related, they actually equal one another. You may notice that I threw a big old triangle in front of H. Anybody remember what the triangle might mean? Okay, now if you said heat, you are correct in terms of use in chemical reactions. But if you're talking about H in terms of mathematical equations, it actually means change. So the change in H is the same thing as Q. So delta H, the triangle is actually considered the uppercase letter delta in the Greek alphabet. So it's pronounced delta H is equal to Q. They are numerically equal. However, their definitions are actually a little bit different. They essentially say about the same thing, but how they are found, how we actually get the values of Q and H, that really becomes what's different. So when you talk about Q, it's actually, we've been calling it heat. Sometimes it's expanded a little bit to be called heat of reaction. It's the value of Q required to return a system to a given temperature. So, the reaction happens and you want to take it backwards. That would be your Q value. This is the big kicker though. It's found experimentally. You have to use experimental data to find it. And then once you find Q, you of course have H, but it's just called Q, I guess, in the meantime. Whereas enthalpy, it's called enthalpy of reaction, or the H, or delta H. It's the net change in heat during chemical reaction. So again, if you look at those two definitions very closely, they really are saying exactly the same thing. But H is found using theoretical values, typically from a table that you will either find in a textbook or online or something like that. So it's about theoretical versus experimental data. When you look a little closer at these, just to kind of drive the point home, we're going to look at this equation here with sodium and water yielding sodium hydroxide and hydrogen gas. This is a question here to pose to you regarding. So if 367.5 kilojoules of heat are evolved in the reaction, is it endothermic or exothermic? Okay, or are evolved, is the reaction endo or exothermic? Okay, so what's the key word we're looking for? Okay, shout it out. Act like you know it. What's the key word that tells us endo or exothermic? Hopefully you said it was the word evolved. Evolved means given off. Evolved means exothermic. So if it's exothermic, what's the sign? Is it positive or is it negative for Q and H? Okay, what's the sign? Hopefully you said negative. So Q would be negative 367.5 kilojoules. Again, it's found experimentally. Whereas your delta H would be negative 365 or 67.5 kilojoules. And that would be actually found in tables of theoretical values that lots of chemists have spent countless hours doing reactions and testing H's and figuring it all out. Now I want you to really think about something. Would you expect, really, in reality, in all truthfulness, would you expect your experimental values of Q to match theoretical values of H? I mean, think about that for a second. In theory, it should be negative 367.5. But if we were actually going to do this experimentally, what are all these things that could happen? I mean, tons of stuff, right? Human error, you could have impure reactants, you could have side reactions, you could spill something. I mean, you could have a million things happen. So this is another thing to recognize, is that there is almost this, error, source of error kind of built into this information. When you do something experimentally, you can compare it back to theoretical values. To see basically how good did I do in my chemical reaction. And weirdly, we're actually going to do that in the lab coming up. So you'll get to see how well you actually did in your reaction versus what the theoretical values were supposed to be. So again, a little bit more theory here, really utilizing the evolved and exothermic and absorbed and endothermic. And that's really it. So we'll talk about it in class. See ya.